Chapter 9, Numerical Methods, Section 9.1, LU-Decompositions. A factorization of square matrix A as A equals LU, where L is lower triangular and U is upper triangular, is called an LU decomposition, or LU factorization of A. So what we're saying is that we'll take some system, say AX equals B, and we will decompose that into two new systems, one UX equals Y, and then LY equals B, where U is upper triangular and L is lower triangular. So we're basically just stopping along Y in the middle in order to get to B. So it gives us an alternative way to solve for X when we solve systems of equations. We can stop along the way to Y. So the first step to do this is first write LU X equals B. So we just replace A with LU. And then step 2 is to do the substitution, Y equals UX. And then we'll write LY equals B, because L times UX is B, and we will solve for Y. After we solve for Y, step 3 is to take what we get from Y from solving this, plug it back in over here, and then solve for X. So we don't solve for X immediately. We solve for Y, and then we plug that back in and solve for X afterward. Let's do an example of that. Suppose we have this LU factorization right over here. So here's A, here's L, and here's U. So A equals LU. And we want to use this decomposition of A to solve the system AX equals B that's given over here. So step 1, we need to rewrite our system as LUX equals B. So we'll pull off L. So that's 2, 0, 0, minus 3, 1, 0, 4, minus 3, 7. Then we need to multiply by U. So that's 1, 3, 1, 0, 1, 3, 0, 0, 1. We then need to multiply by X and set that equal to B. So that's step 1 out of the way. We have LUX equals B. Now step 2 is we should write UX equals Y and solve for Y. So U is 1, 3, 1, 0, 1, 3, 0, 0, 1. We'll multiply that by X. And we'll set that equal to Y. So that's UX equals Y. So now let's solve LY equals B for Y. So for L, we have 2, 0, 0, minus 3, 1, 0, 4, minus 3, 7, and multiply that by Y, and set that equal to B. So that's LY equals B, and this gives us a top equation of 2y1 is equal to 2, negative 3y1 plus y2 is equal to 2, and 4y1 minus 3y2 plus 7y3 equals 3. All I did was read off each of the rows. Okay, so that's not a difficult system to solve because of the fact that L is lower triangular. It makes it much easier. We immediately get that y1 must be 1, just divide by 2, plug that back in, and then we get that y2 is 5, and plug both those into the bottom equation, and we get y3 is 2. So that's the advantage of the decomposition, is that it's easy to solve for y. So now we can go back in and do step 3, which is, now that we have y, we will plug it into the ux equals y equation to solve for x. So we have 1, 3, 1, 0, 1, 3, 0, 0, 1, multiplied by x, and that equals 1, 5, 2, as we now see because we just solved for all of those y's. So that gives us a top equation of x1 plus 3x2 plus x3 equals 1, just by reading off that row. Second equation, x2 plus 3x3 is equal to 5, and x3 is 2. And just like it was easy to solve this equation because L was lower triangular, it's easy to solve this one because U is upper triangular. We immediately have that x3 is 2, and we can plug that back in to see that x2 must be negative 1, and then plug both those into the top equation to get that x1 is 2. So it makes it pretty easy to solve these equations, even though it may be a little bit tedious to do the split. The hard part really is coming up with the split A equals LU. So we have this theorem that if A is a square matrix that can be reduced to row echelon form U by Gaussian elimination without any row interchanges, then A can be factored as A equals LU, where L is a lower triangular matrix. So it's not super difficult to see why this is true. If we were to write EK times EK minus 1, etc., until you get to E2, E1 times A, all of these elementary matrices times A equal to U. So if A could be reduced to row echelon form U by Gaussian elimination, then we'd be able to write A equals E1 inverse, E2 inverse through EK inverse U. All of these E's are lower triangular, so their inverses are lower triangular, and we don't have to worry about them breaking that lower triangular nature because we know that we don't have any row interchanges, so they couldn't have swapped and moved around anymore. Let's take advantage of this theorem and find an LU decomposition of this matrix right over here. So what we have to do is we have to reduce it and keep track of the elementary matrices we're using and their inverses. So it's not super easy. Let's start by taking half of this first row. That way I can get a leading 1. So I'll make the top row 1, 3, 1, and keep the other rows the same. So minus 3, minus 8, 0, 4, 9, 2. And the elementary matrix I used was the one that just has half multiplied by the first row. The rest of the rows are identity. So if I want to invert it, it's easy because it's an elementary matrix. Just multiply by 2 instead of doing the half. Okay, let's keep going. We want to keep reducing it. So how about I get a 0 underneath the 1? So I'll have 1, 3, 1, 0, 1, 3, 4, 9, 2, because I'll just take 3 of this first row and add it to it. So that means that my elementary matrix that does that should be, well, the same for the top row. I didn't modify that. I'm just taking 3 and adding it. So I'll just have a 3 over here. Okay, so that means that the inverse of adding 3 would be subtracting 3. So I have 1, 0, 0, minus 3, 1, 0. And you can either multiply this by E2 to convince yourself it's the inverse, or you could take the inverse of E2 and come up with this. In any case, let's keep going. Let's keep reducing. So I need to get another 0 underneath, so I'll keep my top 2 rows the same. And I'll end up with 0, minus 3, minus 2 by subtracting off 4 on the bottom. So E3 will be 1, 0, 0, 0, 1, 0, minus 4, 0, 1, which means that E3 inverse is 1, 0, 0, 0, 1, 0, 4, 0, 1. Okay, almost there. How about I write, let's see, 1, 3, 1, that's fine, but I need to get a 1 in the second row. I already have it, great. So I need to get a 0 underneath it. So I'll write 0, 1, 3 and 0, 0, 7, because I'll just take 3 of this row and add it to it. So that means that E4 is 1, 0, 0, 0, 1, 0, 0, 3, 1. Okay, so E4 inverse, is 1, 0, 0, 0, 1, 0, 0, minus 3, 1. Okay, almost there. We have still 1, 3, 1 is fine. 0, 1, 3, and then I just need to get a 1 over there, and then this thing will be upper triangular. So 0, 0, 1, all I have to do is multiply by 1/7, and then there we go. This is an upper triangular form that could be our U. So that makes E5 equal to 1, 0, 0, 0, 1, 0, 0, 0, 1/7, and thus E5 inverse is 1, 0, 0, 0, 1, 0, 0, 0, 7. Okay, that gives us L. So now we have that L is just all of these E inverses multiplied by each other. So I have 2, 0, 0 was our first one, 0, 1, 0, 0, 0, 1, multiplied by 1, 0, 0, minus 3, 1, 0, 0, 0, 1. That was E2 inverse, and now E3 inverse was 1, 0, 0, 0, 1, 0, 4, 0, 1, and then E4 inverse 1, 0, 0, 0, 1, 0, 0, minus 3, 1, and last matrix to multiply by 1, 0, 0, 0, 1, 0, 0, 0, 7. And if we do all the multiplication, we get 2, 0, 0, minus 3, 1, 0, 4 minus 3, 7. Notice that all you had to do was take the 2, take the minus 3, take the 4, the minus 3, and the 7. So it's an easy multiplication to do. So that means that we have our LU decomposition. We have A equals LU is equal to 2, 6, 2 minus 3 minus 8, 0, 4, 9, 2 time equals, sorry, that's A, equals 2, 0, 0 minus 3, 1, 0, 4 minus 3, 7. That was our L. And U, we reduced to 1, 3, 1, 0, 1, 3, 0, 0, 1. So yeah, it's way easier to solve for x when you already have the LU decomposition. Let's do one more example and find the an LU decomposition of this A right over here. What we can do, instead of writing out E and E inverse every single time, is we could just write out a lower triangular matrix. Now that we saw that each of those numbers that appeared in L was just something that we could have obtained by keeping track of the operation that we were doing. Remember, it has to be lower triangular, so all of these guys have to be 0. If we keep track of each of these missing numbers in our matrix along the way, then we don't have to write E and E inverse every single time. We could just build it. So let's do that. Let's first start by taking 1/6 of that. So 1 minus 1/3, 0. And then the second row is 9 minus 1, 1, not changing it yet. And we have 3, 7, 5. So what I did here was I took 1/6 of that, so that means that the inverse would have a 6 in it, so I could just put a 6 in for that dot. And then the other ones I still don't know yet. So I'll just fill those in, and I still have my zeros. So you could just fill it in dot by dot, and then you'll build your L. Okay, so let's keep going. So I have 1 minus 1/3, 0, not touching the top row now. I'll subtract off 9, so I'll have 0, 2, 1, 0, 8, 5. I can do both of these at once, right? As long as I keep track of both dots. So for this one, I needed 9 to be subtracted, so that means in the inverse it'll be positive 9. And for this one, I needed 3 to be subtracted, so in the inverse it'll be positive 3. So I filled in 2 of the dots. So I have 6, 9, 3, and then I just have 3 dots left as my placeholders. Okay, getting there. Let's do our next step, and we'll get a 1 over here instead of the 2, so we just have to divide by 2. So let's do that. 0, 1, half, and 0, 8, 5. Okay, so dividing by 2 means that the inverse would be multiplying by 2. So I have 6, 9, 3 still, but now I have a 2 over here for this dot. We just have 2 left to figure out. Okay, so I've got 1 minus 1/3, 0 still. I have 0, 1, half still. Let's see if we can get, how about a 0 over here, and I can get a 1 over here. Because if I subtract off 8, then 2 birds in 1 stone. It becomes 1. So I'll end up with 6, 9, still the 2, the 3, but now I know that this dot should be an 8 because I'm subtracting off 8, and the inverse, that's adding 8. So I just have 1 dot left. this is already upper triangular, so I don't have to do anything. So I can just set U equal to this matrix right over here. I managed to get a 1 without having to do any kind of operation. So if you want, you can think of that as just multiplying by 1. So that fills in the last number. It must be a 1. So I have 381. And that gives us our L. So now I have U and L. So I have A equals LU equals 600,920,381 times 1 minus a third, 0, 0, 1 half, 0, 0, 1.